Yesterday we spent some time talking about a couple of different historical experiments that have been used to measure the speed of light. The first one, performed by Galileo, didn't give us very good results. The reason that it didn't give us very good results is because it relied on human reaction time. Whenever we're dealing with human reaction time, when we're measuring something so fast as the speed of light, doesn't matter what the experiment looks like, it's not going to work out. Human reaction time just not gel with measuring the speed of light. So then we took a look at another experiment performed by Michelson, which eliminated the need to use human reaction time. Now, there could still be some errors in here. The distance is still pretty small, relatively speaking here, but in the end, we eliminate human reaction time, so we are going to, just because of that, get much, much, much better results. Michelson's experiment consisted of two hills, two mountains, Mount Wilson, Mount San Antonio, 35 kilometers apart. On Mount Wilson, he has this light. This light shines toward this eight-sided mirror. Now, this eight-sided mirror ends up, let's redraw that a little bit so we get, there we go. So this light now travels towards this eight-sided mirror. It reflects off of, let's say, side 4, comes down here, reflects off of Mount San Antonio, or at least a mirror on Mount San Antonio, comes back and, well, it wants to reflect off of side 6, but because this mirror is rotating, side 6 isn't where it was before. Still might rotate, or still might reflect off of side 6, but if the mirror is rotated like it's shown in the position right now, then the light is going to reflect up here and not get observed by the observer. We don't see anything. This guy over here on the left-hand side of this doesn't observe anything. We haven't measured anything as a result of that. So what do? Well, if the frequency of this rotating mirror is, say, 200 hertz, we crank up the frequency. We increase the frequency. We increase it, increase it, increase it, until the observer over here actually observes something. Now, when is the observer going to observe something? Well, when this mirror has made exactly 1/8 of a rotation. So instead of it reflecting off of side 4, going down to Mount San Antonio, reflecting off of side 6 like this at some funny angle, rather side 5 has come in to replace side 6. So during the time that it took the light to go from position A to position B and back to position C up here, this mirror must have made exactly 1/8 of a rotation. That's a nice, simple way of measuring time without the need for using a stopwatch or any kind of human reaction time. So how are we going to actually analyze this problem, given that we know the mirror has made 1/8 of a rotation during that time? Well, I want you to always do it this way. Always write down this equation, and always write down this equation. As I was walking around yesterday when you guys were working on problems, some people are trying to skip steps. Some people are trying to do it in a less than structured way. Trust me. Trust me. At this point, I know more than you do. In 30 years, you may very well know more than me, because in 30 years, I'm probably going to be forgetting everything. Okay? But right now, I know more than you. Trust me. Write down these two equations. Write this one down on the left side, write this one down on the right side. Especially for this, because this is such a recipe problem. Okay? We can solve this problem the same way every time. Okay? Lots of times we got to think really, really hard about a question. Not so much about these. We just follow the recipe, and we're going to answer this correctly. So let's follow the recipe. Okay, sub in your numbers, solve for something. What are you almost certainly going to solve for first? Like 999 times out of 1,000, you're going to solve for t, either big T or little t. What would a little t represent in this experiment? Little t is the, go ahead, Nick. Yeah, it's the time for 1/8 of a rotation. It's the smallest time. Little t is the smallest time. Big T is the time for one complete rotation, or it's the biggest time. So if you ever forget which one's which, just look at the letters, right? Little t is the smallest time. Big T is the biggest time, the time for one complete rotation. Now, you're going to solve for one of these times first, either a little t or big T, and it's like the grass is always greener on the other side. We're never happy with what we have, right? We solve for little t, well, we want big T. We solve for big T, we want little t. So get the other one. Whatever one it is that you solve for, get the other one. If you've got little t, then you would multiply by 8 to get big T. If you've got big T, then you would divide by 8 to get little t. Now, when would I ever change that? When would I ever change what I just did there, multiplying by 8 or dividing by 8? Austin? Sorry? Yeah, if you get a 12-sided mirror, then you're going to multiply by 12 or divide by 12, right? Okay. Same kind of idea, though. You just have to pay attention to how many sides in the mirror it is. Usually, almost always, it's 8 sides. Sometimes in our practice questions, we get 12 sides or 6 sides or whatever the case may be. So solve for time, get the other one, and then sub it back in and get what you're actually looking for. Usually, that's going to either be the speed or the frequency, but it could sometime be the distance, I suppose. Can't really be anything else. All right? All right, let's take a look at the questions that we had on our worksheet. Worksheet number 14. Give you some answers to those, and then we'll go over anything that we need to go over. All right, if we don't need to go over any of those questions from worksheet number 14, let's take a look at 1 or 2 of the questions from page 650 that we had for homework. I think I want to go over question number 2, for sure. Anybody want to go over number 3, or are we okay with that? Yes?
No, sorry, I meant
2, okay. Yep. Anybody else for another one? All right, we'll just take a look at number 2 then. Number 2 says light reflected from an 8-sided mirror. 8-sided set of rotating mirrors travels 15 kilometers to a distant fixed mirror and back. At what frequency is the set rotating if it's turned 1/8 of rotation before the light returns? So this is a typical Michelson experiment, except that the distance isn't anywhere close to what he used, right? He used 35 kilometers there, 35 kilometers back. Okay, we're using 15 there and 15 back this time. That's the only real change. Okay, so what do we do first? We better know what to do first. It's the same thing every single time. Write down the 2 equations, V equals d over t, and t is equal to 1 over f. Don't make this a big T, don't make this a little t. Okay, make sure that you specify which one it is. Now, little t stands for the time for 1/8 of rotation. Big T stands for the time for 1 complete rotation. You can put those subscripts in or not. Doesn't really matter as long as you recognize what each time means. All right, one thing that we need to know here in order to solve for frequency is the speed. What speed do you think we're going to use, even though it doesn't mention it in the question? Yeah, in the absence of being given the speed, when we're looking for frequency, we're going to have to assume that the speed is the constant accepted value, 3 times 10 to the 8 meters per second. Now, my distance traveled here is going to be 30,000 meters. And the time for 1/8 of a rotation here is, well, t 1/8, whatever that works out to be. I think we need to divide 30,000 by 3 times 10 to the 8. I think you end up with 1 times 10 to the minus 4. Is that right?
Yep.
That's a pretty typical time for little t. We don't necessarily get 10 to the minus 4, but we usually do end up getting 10 to the minus 4 for that. Now, what do I do with that? Yeah, remember what we said? The time that we get is never the time that we want. So let's times it by 8 to get the time for 1 complete rotation. Big T would therefore be equal to 8.0 times 10 to the minus 4 seconds. Let's sub that in over here and solve for the frequency. Frequency goes up, 8.0 times 10 to the negative 4 goes down. We take the inverse of 8. I think it's 0.125. I think it's going to be 1250, isn't it? 1.25 times 10 to the 3 hertz. Now, I don't know if you remember this, but yesterday I said usually we end up getting in the range of 500, 600, 700 hertz. Remember that? You know, sometimes a little bit higher. But it's almost always 10 to the 2. We get 10 to the 3 here. Like, this is twice as big as what we usually end up getting, right? Anybody want to suggest maybe why we get a correct value? It is correct. A correct value that's about twice as big as what we usually get?
Because the distance is so small.
Because the distance is about half, right? Not exactly, but about half. So, of course, the frequency is going to be about roughly twice. That make sense? Yeah? All right, you will have, at some point during this class, there'll be a practice question set go up on, it's got Michelson's experiment. It's also got a little bit more stuff on there as well that we're gonna do today. That will be homework for Monday for you. And that's probably gonna end up being your only homework for Monday, okay?